I always try to give you guys the heads up when the big calculation from the unit is coming up, and that's today. It's a return to ice charts, but using ice charts to calculate pH and related quantities for an acid, but specifically a weak acid. We've looked at pH of a strong acid, which ionizes completely. You know that weak acids, they do ionize, but not the whole way. We're going to look at something called Ka, which is a measurement of how much a weak acid breaks down, and use that and an ice chart to calculate pH. First thing, you are able to write a Kc expression for dissociation of a weak acid. Set up the equilibrium, and if you notice in the packet, ignore water because it's a liquid. You can write, and you'll see this a lot, I usually do it, H3O plus is usually written as H plus. It's just H plus hanging out with a water molecule. Nobody cares about water anyway. So if I write a Kc expression for this reaction, this dissociation of a weak acid, H plus, A minus on the top, or H3O plus and A minus on the top, my product as written, HA, the original undissociated acid on the bottom. And we're good. We call this Kc in general because it uses concentrations, but Ka is more specific. Is it wrong to call it Kc? No, but you're going to be able to look up or be given Ka values. So if you see an acid, call it Ka. The larger the value of Ka, the more completely the acid breaks down. That makes sense because you have products on the top, reactants on the bottom, more products, bigger Ka. So this happens quickly. We're going to be able to calculate the pH at equilibrium because this happens so quickly. It's not like the weak acid waits and 3 days later it breaks down. Percent ionization is another measurement of acid strength. You have one practice using it. It's not as important as Ka. This is not your big calculation. So I set it up for you. It's going to be the concentration of your ionized substance over your initial concentration times 100, like percent always is. It ends up working out to little number over big number times 100, just like always. So in your practice, we had a 0.025 solution of formic acid with a pH of 2.69. What I did is I used the 2.69 pH, 10 to the negative that, to give me my concentration of hydrogen, which is my molarity, which is the lower of the numbers. That's how much is broken down because it breaks down into the hydrogen ion. Divided by 0.025 times 100 gave me 8% ionized. No big deal. Okay, that's great. Do we use this? You could. Do we use it often? No, this next thing is the big idea. Using Ka to calculate pH along with an ice chart. Write your ionization equation or be given it. Use your equation for Ka, which we know how to do. Put your values into the ice chart and let's solve. So I set up sort of a shortened version of the problem for hypobromous acid, which is in your packet. If you want to watch this and then try to do the next one on a spare sheet of paper, even though it's done in your packet, you'll see. I may even stop this video after this. I don't want the video to be too long, and do polyprotic acids and the second practice as a second video so that I don't have to edit. All right, so there's my instructions, 0.2 molar. Hypobromous acid, which I don't know what that's for. It doesn't matter. It's an equation. Remember, I can ignore water, and I see water on the left. Water's in the reactants. Sounds great. So I write my Ka expression. H3O plus or H plus. OBr, I don't know why not BRO minus, whatever. I guess the negative charge truly goes to the bromine, but I don't often bother to shift that around. My initial concentrations, where I'm starting with, you know this. 0.2 molar from my problem, and I throw it in water, so I start off with this and none of either of those. Time for change. Time for change. I'm going to lose HBRO and make H plus and OBr minus. That's what I do. So my equilibrium concentration, remember this happens fast, 0.2 minus X molar and X molar and X molar. Sweet. So let's set this up with Ka. I know Ka, and you should still be able to see this at the bottom. 2 times 10 to the negative ninth equals x is h, x is OBR. We're going to divide by 0.2 minus x, molar on the bottom, and I see a problem. I see a quadratic equation coming up here because of x squared and pulling x out of that. I'm fine with it. I have a quadratic solver I programmed into my big boy calculator. If you're interested in that, there are going to be quadratic examples that you're solving in practice problems. I remember asking my high school chem teacher, what happens if we get one of those on a test and we don't have a calculator that solves it? And he looks at me and goes, no one's going to give you one of those on a test. I was like, okay, cool. So if you ever are taking an AP Chem test, or the AP Chem test, or you're taking one of mine, I'll tell you not to expect to have to solve a quadratic equation on the exam. I expect you to on a practice, especially when you can Google a quadratic solver. No problem with that. He just looked at us like we were idiots and said, no one's going to ask you to do that on a test. So expect examples that don't. How do we get to an example that doesn't? You are sometimes able to ignore x. Just like I'm sometimes able to ignore, no, I'm just kidding. You're able to ignore x, but people tell you when you can do this differently. And he, the same teacher, was like, there's no real rule, but I found some guidelines. Here's my favorite on the guidelines of when we can ignore x. If I take my lowest concentration, 0.2, and divide it by Ka, the dog says yes, 2 times 10 to the negative ninth. If I divide that, my concentration by my Ka, and I get a number that's over 500, which I'm definitely going to this time, x is going to be small enough to ignore. So when I set this up, instead of getting a quadratic, I'm able to ignore the bottom minus x. So instead, as your packet shows, I end up with 2 times 10 to the negative ninth times 0.2 equals x squared. That gives me a value for x. Looks like 2 times 10 to the negative fifth, which is my concentration of hydrogen because hydrogen is x. I can get the pH here as negative log of my concentration of hydrogen ions for a pH of 4.6. That's it. That's how that goes. So, in terms of calculating these, it's not too bad if you can ignore x. There's not that much different. Setting up your ice chart, find what you have, take it away and make what you don't have, set up your Ka equation, and solve. So I'm going to hit pause here. I'm going to start a new video on polyprotic acids and another example. The examples run a bit long, so I don't want to make you watch me erase and make you watch me edit as I run out of time. See you in a bit.